Everyone is focused on making GPUs faster. NVIDIA releases a more powerful GPU, companies buy thousands of them, and AI models become larger. But at this scale, the problem is no longer just how quickly one GPU can calculate. The problem is how quickly thousands of GPUs can send their results to one another. Because a large AI model does not sit neatly inside one GPU, its work is divided across entire racks of GPUs. One GPU calculates one part and then another calculates the next part. During training, all of them repeatedly exchange results and update one another. So, you can have some of the most expensive processors ever built waiting for data to arrive. And the technology being introduced to fix this is photonics, using light to connect GPUs. Let us start with how GPUs are connected today. Take NVIDIA's GB200 NVL72. It places 72 Blackwell GPUs inside one rack and connects them through NVLink. Within that rack, NVIDIA uses passive copper cable cartridges. And that makes sense. Copper is cheap, reliable, and extremely effective when the distance is short. But the largest AI systems need far more than 72 GPUs. Companies connect rack after rack after rack until the system contains thousands or potentially hundreds of thousands of GPUs. As signals travel farther at very high data rates, copper connections become less efficient because the signal weakens and becomes distorted. Engineers add extra components to strengthen and correct it, but these consume more electricity and produce more heat. Copper still works, but the problem is that moving increasing amounts of data through requires too much power. So, where does photonics enter? The GPU performs the AI calculations using electronic transistors. After a GPU finishes its part of the calculation, the result leaves the GPU as an electrical signal. It travels through the network card and reaches a network switch. Before being sent to another rack, the electrical information is passed into an optical transmitter. A laser supplies a beam of light. A tiny component called a modulator changes that light according to the information coming from the GPU. The modulator can change the strength or phase of light billions of times per second. The light now carries GPU's data. It travels through an optical fiber. At the other end, a photodetector receives the light and turns it back into an electrical signal. The next GPU can then use that information. So, photonics replaces part of the route that data takes between GPUs. People often explain this by saying light is faster than electricity, so photonic connections make computers faster. That is not quite right. Electrical signals also travel through wires at a substantial fraction of the speed of light. And inside a data center, the distances are not long enough for the basic travel speed to be the main issue. The important advantages are how much data light can carry and how much power is required to carry it. An electrical connection carrying extremely fast signals needs more equipment to prevent the signal from becoming distorted. Light can travel farther through fiber without requiring the same amount of electrical signal connection. And a single fiber can carry several different wavelengths of light at the same time. This is called wavelength division multiplexing. It is useful because one optical connection can carry several large streams of data together over longer distances while avoiding some of the power-hungry electrical equipment required by copper. Optical fiber is not new. Large data centers already use removable optical transceivers to connect servers and switches. In traditional systems, the switch chip creates an electrical signal that travels across the circuit board before being converted into light at an optical module. As network speeds increase, even the short electrical journey consumes significant power. Co-packaged optics solves this by placing photonic engines beside the main switch chip. The signal travels only a tiny distance before being converted into light, reducing power use and the need for additional electrical components. NVIDIA Spectrum X Ethernet Photonics places optics beside the switch ASIC. Copper can still be used within a rack, while optical links connect larger groups of GPUs across racks. NVIDIA announced on May 31, 2026 that the system had entered production for its Vera Rubin platform, with broader availability expected in the second half of 2026. Broadcom's Tomahawk 6 Davison uses a similar design, combining co-packaged optics with a switch capable of handling 102.4 terabytes per second. Intel has also demonstrated an optical input-output chiplet placed beside an electronic processor. Its 2024 prototype transferred up to 4 terabytes per second in each direction. This is the more futuristic side of photonics. Light does not only travel through a chip. When light waves meet, they can strengthen or partially cancel each other, a phenomenon called interference. Engineers can control this interference using tiny components built into a photonic chip, allowing light to perform mathematical operations. In a simplified example, the brightness of a beam represents a number. A brighter beam represents a larger value, while a dimmer beam represents a smaller one. Adjustable optical components then change the beam's strength or phase according to an AI model's learned weights. Several beams are combined, and their interference causes them to add together or cancel one another. A detector measures the final light, and that measurement becomes the result of the final calculation. Instead of electronic transistors repeatedly multiplying and adding numbers, the system arranges the light so that the physics of interference performs part of the calculation naturally. This is especially useful for matrix multiplication, one of the main calculations GPUs perform repeatedly when running neural networks. Does this replace the GPU? Not yet, and probably not completely. Photonic calculations are usually analog. The answer is represented by the strength or phase of a real beam of light rather than a perfectly defined digital number. This means small manufacturing differences and temperature changes can affect the result. The laser also requires power, and after the light performs the calculation, the output usually has to be detected and converted back into an electrical signal. Neural networks also contain many operations that are difficult to perform using only light. So, a photonic processor cannot simply replace a modern NVIDIA GPU and run all existing software. A more realistic system would use both. The GPU would control the program and handle the operations. When it reaches a very large matrix multiplication, it could send that calculation to a photonic accelerator. The light would perform the multiplication, and the result would be converted back into an electrical signal and returned to the GPU. Researchers are building more complete photonic neural network systems, but for now, they remain specialized accelerators and research demonstrations rather than general replacements for GPUs.